Differential calculus is the study of rates of change of functions. We talked about in the limit section that if we had the limit as h goes to 0 of f at x plus h minus f at x over h, that this was an instantaneous rate of change. These are the kinds of rates of change that we're talking about for differential calculus, these instantaneous rates of change. We're going to find there's lots of easier ways to calculate these instantaneous rates of change than actually going back to the limit. But for now, we're going to start with the limit, and we're going to use this to define something called the derivative. We write the derivative as f prime at x most of the time. On page 97 in your book, you'll see several other ways that we write your derivative. The two most common that we'll use will be f prime at x and this dy dx. This is mostly for what we call differential equations. But we use these derivatives, this derivative here, to calculate instantaneous rates of change. This definition right here for a derivative needs to go on your index cards because it is very, very, very important. If this limit exists, then the function has a derivative there, and it's said to be differentiable. Now, how do we find the derivative? Well, we just use this limit, for now at least. So if we have a function, let's say we have f of x equals negative 4x plus 6. Now this one, you should be able to look at this and know what the instantaneous rate of change is at any point. Why would you know that? Well, what did we talk about with the rates of change? We said that an instantaneous rate of change was the slope of the tangent line to the function at that point. Well, what kind of a function is this? It's a linear function. So for a linear function, anything tangent to it is on it. So the slope of this line is the same as the slope of all the tangents. So you should get negative 4. So let's see how we calculate that out, just to make sure that we can understand this definition here. So this is the definition of a derivative. It's the instantaneous rate of change, this limit. So we take our function and we plug in negative 4 times x plus h plus 6 minus negative 4x plus 6 all over h. And we're still calculating the limit. So now we just simplify. So we have negative 4x minus 4h plus 6 plus 4x minus 6. So these cancel and these cancel. And then the h's cancel. And you see that just like we thought, we got negative 4. But you see how we calculate it out by plugging it into this limit. So let's try one more. Help if I gave you the function first, wouldn't it? So we have the function x squared plus 3x plus 5. If we want to find its derivative, we go to the definition of the derivative. Because the derivative is telling us the instantaneous rate of change, which we know is the slope of the tangent line, which is this limit here, because remember we took the limit of the slope of the secant line. Get closer and closer. Make sure you've got all that with the tangent lines. So we plug this in. All over h. Now, this is where it gets a little bit tedious because you do have to multiply it out and simplify it to be able to solve it. So we've got x squared plus 2xh plus h squared plus 3x plus 3h plus 5 minus x squared minus 3x minus 5 all over h. So those cancel, and those cancel, and those cancel. And we can factor out an h from what's left at the top, and we have 2x plus h plus 3 all over h. Cancel those out, and we get left with 2x plus 3, because we take the limit as h goes to 0, so that one goes to 0, and we're left with 2x plus 3. So the derivative of this function is 2x plus 3. So what that means is, when we have this parabola, the tangent line is given by this line here. The slope of the tangent line, sorry. The slope of the tangent line at any point. The slope of the tangent line at any point x on f of x. I guess the point would be, we should be more specific and precise, x comma f of x on the function f of x. So this here gives us our slope. So if we ask ourselves what's the instantaneous rate of change at x equals 1, that would be the derivative at 1. So we'd have 2 times 1 plus 3, which is 5. So the instantaneous rate of change at x equals 1 on this parabola is 5 units per whatever the unit is that we're using. Now, sometimes we'll use a little bit different definition. If we know that the derivative is the limit as h goes to 0 of f at x plus h minus f at x all over h. Remember, when we drew our picture, we had this function, and here is our x, and h was this in between here, and it kept going closer and closer to this, so that our line that we were drawing, our secant line, kept getting closer and closer to what the tangent line would be, the slope of the tangent line. Now, if we want to use a little bit different definition, say we want to find the derivative at a specific point. Then we would say the derivative at that point is equal to the limit as x goes to that point of the function value minus the function value at that point over x minus a. Now, does this make sense? Well, let's look. So let's say we have x is here and a is here. If we draw in our secant line, hopefully you can draw a straighter line than I can. If you draw in your secant line, then the slope of this secant line, well, what is it? Well, this point here, we've got f at a for our y value, and here we have f at x for our y value for this point. So to find the slope of the secant, rise over run, so this is the slope of that secant line. The difference of the y values over the difference of the x values. But we don't want the slope of the secant. We want the slope of the tangent line at a. So we want the slope of this line here, this tangent line. So what we do is we take our x closer and closer to a until we get to this tangent line here. So that will give us the slope of the tangent line specifically at that point A. So here we're going to use this to get a general equation like the last one we had used, so that we can find a general equation, and then we could just plug it in any numbers we want for the derivative. And this one we're using at a specific point. So make sure you have both of these equations, both of these definitions for a derivative on your cards. So for example, let's say we have f of x equals the square root of 2x. Well, what if we want to know what the derivative is at 8? So we take the limit as x goes to 8 of f of x minus f at 8 all over x minus 8. So we have the limit as x goes to 8 of the square root of 2x minus, well, 2 times 8 is 16, square root of that is 4 over x minus 8. And if the limit is going to 8, then we need to figure out how we can find this limit. Well, there's lots of ways we can kind of make this work. Basically, we need to figure out how to get this x minus 8 out of the bottom. So we need a factor of x minus 8 in the top. Well, we can't just make it up, so we have to multiply by 1 in disguise. And I know you guys think I just pull these things right out of the air, but if you look at this top part here, you'll see that if you square this one and square this one, you have 2x minus 16. And then I could factor out my 2, and I'd have that x minus 8 to be able to cancel it. But how do I get that? Well, I have to multiply by 1 in disguise because I can't change anything. But in order to get this function to look like something where I've squared both things, that's what I have to multiply by. The same thing with a different sign. So I multiply that through, and I get 2x minus 16 on the top, just like I wanted. And then I have x minus 8 times the square root of 2x plus 4 equals, and then, forgot my limit again. Limit as x goes to 8 of 2 times x minus 8 over x minus 8 times the square root of 2x plus 4. Cancel those out. The limit as x goes to 8 of 2 over 2 times the square root of 2x plus 4. So now I can just plug in 8. So I haven't changed the function. I haven't changed the equation at all. All I've done is rearranged it so that I can find the limit. So I rearrange it in such a way that I can find out what the limit is by plugging it in. So if I plug in 8 here, I get 16, square root of 16 is 4, 4 plus 4 is 8, so I have 2 eighths or 1/4. So the derivative of this function here at 8 is 1/4. So what does that mean? That means that the slope of the tangent line, or the instantaneous rate of change when x equals 8 on this function, is equal to 1/4. Now sometimes, just like we had one-sided limits, we're going to have one-sided derivatives. So we could have our right hand would be the limit as h goes to 0 from the right of f at x plus h minus f at x all over h. Now I should point out that you really don't have to know both definitions to be able to calculate this, because if I want to find the derivative at a specific spot, I can put that number in here for x, just like with the a, but that's kind of a side note. So if we find our limit from the right-hand side, then that's the derivative from the right. Or if I find my left-hand limit as h goes to 0 from the left, then I'm finding my derivative from the left. So why would I need to find left and right derivatives? Well, there's always a reason. Those beautiful piecewise functions that you all love so much. Let's say we have this piecewise function, and we want to find at the right and left-hand derivatives of this function. So we take, let's say we do start with the right. So we take the limit as h goes to 0 from the right. We're looking for the derivative at 1. So we say f, write our definition down. I suggest every single time you do one of these problems that you just write the definition down before you start trying to fill it in, because that will help you memorize it and it will help you understand exactly what you're doing. So from the right, we're going to be on this part of the equation here. So we have 3 times x plus h minus, now, here's where you have to be careful. The function value at 1 comes from this one here. So that's 1. And we're looking at x equals 1. So we can go ahead and plug in a 1 there. So our f at x is just going to be 1. Because we're looking for f prime at 1, that means we use x equals 1 for plugging in here. So we have this limit that we need to calculate of 3 plus 3h minus 1 all over h. And we can simplify that. We get the limit as h goes to 0 on the right of 3h over h plus 2 over h. So those h's cancel. And here we have, remember, the limit of sums is the sum of the limits. So this one goes to 3, but this one, will help if I wrote it correctly, of 2 over h, the limit as h goes to 0 of 2 over h is infinity. It doesn't exist. So what is this limit? Well, 3 plus infinity is just infinity. So this limit doesn't exist. So the derivative from the right does not exist for this function at x equals 1. Now from the left, again, write that definition down every time. This is one of those key and important things. So we're looking at when x equals 1, and we're coming from the left this time. So we're going to have 1 plus h cubed minus 1 over h. And yes, you need to multiply that whole thing out. So you get 1 plus 3h plus 3h squared plus h cubed minus 1 all over h. And then you notice these 1's cancel. And we can factor out an h so that we have h times 3 plus 3h plus h squared all over h. So those cancel. So now we look at this limit, and the limit equals 3. So the derivative of this function at x equals 1 doesn't exist. So there's no tangent, no slope of the tangent line there. The derivative from the left, the slope of the tangent line is 3. Now, what does this mean? Well, what we've got here is we've got this function that goes like this, and then at x equals 1, it jumps and shoots off like this, probably. That's a better way to put it. But it jumps. So we can't take the derivative of the function because we can't have the limit of the function. So here we've got a really steep derivative, and here we don't have one at all. So, derivatives. Derivatives are the slope of the tangent line of a function, it gives us instantaneous rates of change. We will spend the rest of this quarter, the rest of this semester, on derivatives. Derivatives are a huge thing with calculus. All of differential calculus is based on using derivatives, which is based on using the limits. So make sure you understand all the limits and how we get those tangent line slopes from the limits and how we can compare them with the secant lines. Make sure you understand the relationship between the tangent line and a derivative and what that means. Make sure you've read section 3.1 in your book and written down any questions you have so that you'll be ready to ask them in class.